Okay, just move to my first slide. Just very quickly, if I'm sure most people know about AdaCore, if you want more information about us, we have obviously we have a website you can go and look at, but we also have a virtual booth that Emma talked about at the beginning, and I'd encourage you to go and have a look at that. The work that I'm going to talk about today has been done through the high class research group. This is a joint industry and UK government funded research initiative looking into cybersecurity for civil aerospace. And some of you may recall Mike Bennett's presentation back in 2019, I believe, at HIS, where he talked about the work that's being done here. If you want to learn more about high class, there's a link to a blog post at the bottom which will tell you about the work AdaCore is doing. But there is also a high class virtual booth, and I'd encourage you to go and have a look. There's some great tech coming out of this research group, and you can find out lots more information by talking to the people on the booth. Okay, so what do we mean by airworthiness? And this isn't meant to teach anyone to suck eggs at all. I'm aware the audience are probably very knowledgeable about this subject matter, but in a nutshell, airworthiness is all about ensuring that the risk of a failure with any of the components of your system that make up the full aircraft, where those failures could lead to a safety hazard, which could have a direct impact on any humans involved in the flight. We want that risk to be as low as reasonably practical. And the reason for this is pretty obvious. We want to make sure our air travel is safe. But we also need to ensure we can convince our regulatory authorities that it's safe. And here we're talking about organizations like the FAA, who check that the air corridors across the US are safe, and EASA, who do a similar thing across Europe. And one thing we can do is an approach like what we've got here, which is an extract of a goal structured notation argument. And what we'd have is a top level goal that would talk about how our air vehicle is safe because the risk of a failure leading to a safety hazard is as low as reasonably practical. And then we break that down into sub goals, and we provide evidence to support those claims, and we describe the context that we're making those claims within. And at this point in the argument, as we can see on this slide, we're talking about, is our avionics software safe? And one way we can go about doing that is by referring to standards and guidelines that our regulatory authorities have stated are an acceptable means of compliance with the safety requirements that they've stipulated within things like advisory circulars that they'll pass around. And DIR 178C, which we've heard about already, is an excellent example of that. So if we can show that we meet the objectives within things like DIR 178C, we go a long way to argue that our system is safe. And the industry is very good at doing this. I think the audience will be people who will be very involved with avionics systems development, and will agree that we generally know what we're doing here. So if software safety processes are mature and they've been around for a while and we know what we're doing, then is there any need for an airworthiness security process? And one bit of research I found when I was looking around for articles for this talk was a keynote that was given by Robert Hickey during the CyberSat conference in 2017, where he stated that his team in the previous year of 2016 had established a remote presence on board a civilian aircraft. And what was fascinating about this was that the aircraft was parked on the runway at Atlanta City Airport, and they didn't need to establish a physical presence. They didn't need to touch the aircraft. They did this remotely, and there was no insider threat. And the article, which I'll provide a reference to at the end of these slides, goes on to imply that the OEMs that developed the avionics systems were aware of the vulnerability that was being exploited. And it does make you wonder, well, if the vulnerability was known about, why wasn't it dealt with? Why wasn't it fixed? And I've given 5 reasons here that I can think of. I think probably one of the biggest reasons is point number 5 here, which is the cost. And Robert Hickey did go on to say in that keynote address that the cost to change one line of code on a piece of avionics equipment is $1 million and will take a year to implement. And I think in this context, he's talking about deployed software here. So you can see that if you've got a complex vulnerability that you need to patch in deployed avionics, and maybe you need to ground a fleet of aircraft and swap out components, it's going to get very expensive and it's going to take a lot of effort. So one of the reasons the industry could have found itself in this situation where it felt it needed these additional guidelines is to do with the terminology, the well-known terminology within the safety guidelines. And one such term that most people will be aware of is a failure condition. And this is all about the effect that some event can have on the aircraft, where that effect can have a direct consequence to the humans or the airplane itself in a kind of safety hazard environment. And it does say that these conditions can be started from external events. And that could, in theory, cover cyber attacks. But when you then start to look at what the industry means by an event, it's more about environmental circumstances like bird strikes and cabin fires, etc. So if it wasn't ever intended to cover cyber attacks, then there's potentially a bit of a hole in the process here. So the way the regulatory authorities dealt with this is that they asked two groups, namely the RTCA and EUROCAE, to form a joint working committee. And they then went about producing two sets of guidelines, namely ED202A and DO326A. And one of the first things they did is that they came up with a new term called threat condition. And this is similar to a failure condition, but now we are explicitly talking about acts of intentional unauthorized electronic interaction involving cyber threats. So we've already heard from Paul Waller earlier on about how the terms safety and security can get confusing. And in the context of civil avionics, security is about threats which are human initiated, and these are intentional acts. And then safety is all about events which are more environmental and failures and errors which we consider to be accidental. And another thing we tend to stumble over when we're thinking about safety and security is what behavior do we exhibit following a failure? Do we fail safe or do we fail secure? And those conditions can have very contradicting circumstances. And there are other failure behaviors that we could possibly think about. But when we're talking about the airworthiness security process, we are very much talking about security threat conditions that could lead to safety incidents. So the purpose of aviation, security is all about the safety of flight. And of course, we want to fail safe, but more importantly, we're aiming for a very high fault tolerance. And we're making an argument to show that the risk of our system failing is as low as reasonably practical. The process itself is made up of 7 key stages. It's arguably not the most straightforward of processes to go through. It's certainly not linear. It's more like a spiral that jumps around quite a lot. It has some similar aspects to what you may be familiar with safety software development, in that it has a plan for security aspects of certification. And this is where we're going to stipulate how we're going to complete our security development, how we're going to test our security measures, and how we're going to show we've got some security assurance to the desired level. One area I want to talk about a bit more is the security development phase. And inside of here, we have an activity called security verification. And this includes 3 main activities, and 2 of them are security effectiveness assurance and the identification of vulnerabilities. And this is quite interesting to me because this feels quite new in the world of avionics. And the guidelines that have been produced to support ED202A and DO326A talk about a new activity called refutation. And this includes a number of activities, 4 of which are explicitly stated within the guidelines. And this goes back to what Mark and Mike were talking about the effectiveness of testing techniques. There is no one testing technique that's being recommended here. It's recommended that a whole host of these negative testing techniques are utilized. So refutation is made up of penetration testing, static and dynamic code analysis, formal proofs, and fuzz testing. And there may be other techniques that are applicable. But fuzz testing is what I want to talk about a bit more today. So the standard, like a lot of security standards, encourages a defense in depth approach. So this is where we've identified our security perimeter and our environment, our security environment, where we're saying that's where our attackers could start their attack vectors across our security perimeter to try and infiltrate our security assets. And once we've identified those assets, we wrap them with security defensive measures. And we do this in such a way that we can argue that they're independent of each other and there's no common mode failures. And fuzz testing can play multiple roles here. It can be used to assess the effectiveness of those security measures, but it can also arguably identify them as well, because it's a very good technique for identifying software bugs. And if those bugs are such that we can't actually fix them, but we need to put defensive measures around them, then they become security assets. So what exactly is fuzz testing? Well, it's a good way of thinking about it is to consider the difference between robustness and verification. And one way of describing this, I'd like to introduce you to something I've been working on at AdaCore, which is a Smoothie Maker. Now, this Smoothie Maker is quite straightforward. We've got a great big funnel on the left. We're going to drop fruit in, and then we turn the tap and we get some smoothies out. But there is a secret ingredient inside. And we've got some security requirements. We need to make sure this machine is operational at all times. This is really important because our engineers are thirsty. We want to keep them hydrated. And we also want to make sure that secret ingredient is kept secret. So like all good engineers, I've got a test plan. My verification strategy is quite straightforward. I've got some very basic requirements. They're along the lines of, if you drop a banana in, you get a banana smoothie out. So I can go ahead and do that. And I can put all the bits of fruit in and I can check I get all the correct smoothies out. So fuzz testing is different. We don't really care about the output anymore. Fuzz testing is more like going into your kid's bedroom and opening a random drawer and grabbing a handful of the weird and wonderful things that are in there and just chucking them into the funnel. And then let's stand back and see whether the machine can stand up to that those test conditions. And robustness may not be the best category to put fuzz testing under, but there are lots of different terminology statements that fuzz testing could come under. Vulnerability testing is definitely a key one, as is refutation testing in this context. So what we're looking for here is the behavior of the system when we subject it to test conditions that it may not even be used to dealing with. Can it stand up, or does it blow up in flames? And such that we've now got a denial of service and we've broken that first security requirement. Or does our secret recipe get exposed? You know, can the bug be leads to important data being leaked out of our system? So fuzz testing is an automated security testing approach. You provide the fuzzer with a set of test cases known as the starting corpus. The fuzzer will mutate these into more test cases. And it's all about detecting anomalies in that application that we're testing. We can perform it at the unit level or the system level. We can scope it how we want. It's not about verification. It's not about checking that the output of the system matched some expected output. And our processes that we're testing have to terminate. We need to execute a huge quantity of test cases with fuzz testing. They need to be able to terminate very quickly. We need to be able to execute the test to completion in as short amount of time as possible. There's lots of different flavors of fuzz testing. One of the most interesting ones is smart grey box fuzz testing, and this is where we understand the path of execution through the control flow graph of the system we're testing. And this allows us to focus the mutation engine on those test cases that find new paths, and we can explore more of the control, the code base. So as I previously said, the guidelines present this new area called refutation. And refutation is a very deliberate negative take on verification testing, and it's designed to try and get you into the mindset of the attacker. Within High Class, we have a working group that's looking at security standards within civil avionics. And one of the things they did early on was they did a gap analysis report. And this resulted in an issue stating that the guidelines for refutation testing are lacking. And some of the points that were raised here kind of resonate with the talk that Mark and Mike gave earlier. In particular, with these new types of testing, how do we measure quantity and quality? How do we know when we've done enough? And what are we testing? Is it the unit level, the system level? Choice of programming language is interesting. If we're talking about fuzz testing, it's all about what anomalies can we detect in the system. Ada's got a really rich runtime constraint checking capability and can detect things like buffer overflows. And languages like C, we may need to switch on things like address sanitizers to get the same effect. So industry was asking for additional guidance through High Class, and AdaCore's produced a tech paper called Guidelines and Considerations around Refutation Testing Objectives to try and fill this void. So the technical paper takes those main missing elements and has turned them into 30 considerations. And then we've provided an annex to cover fuzz testing. And one of the things that we state in this is that when you're putting a plan for your fuzz testing campaign into your plan for security aspects of certification, you need to stipulate how you're going to define your starting criteria as well as your stopping criteria. So the starting criteria is all about measuring the quality of your starting corpus. And here we talk about aiming for 100% statement coverage. And then the stopping criteria is an algorithm that determines how long you're going to run that campaign for. So what I'd like to introduce you to GNAT Fuzz. This is a tool that we've been producing through High Class. It's trying to satisfy the refutation testing objectives within the airworthiness security process. It uses an open source fuzzing technology called AFL++. This is a smart grey box fuzzing technology. And if we lift the hood on GNAT Fuzz, it's made up of a series of modules, some of which we already had within AdaCore, others we've developed through High Class. Libadelang is a tool you may be aware of. It understands the semantic analysis of Ada programs, and you can pass an Ada project to Libadelang, and it will produce an abstract syntax tree that you can traverse and query, and you can use it to generate more code from. So we use it quite heavily within GNAT Fuzz to fully automate the production of the fuzz test harness. And we also produce the build scripts for building and executing the testing campaign. And then we also have a concept of building a starting corpus. So we analyze subprograms within Ada packages that we can fuzz test. And we build up a starting corpus based on values associated with the types of the parameters of those subprograms. Quite early on, we produced a GCC compiler pass that adds instrumentation around the basic blocks during the compilation. And this is what AFL needs to understand when a test case has just found a new path through the control flow, and it will put that test case back on the queue for further mutation. We've got a runtime library that interfaces with the C AFL runtime. And here we can switch between the different AFL operating modes of deferred and persistent and the other flavors it supports. And this is also where we automate the encoding and decoding of ADA variables into binary test case files. And then we also have the concept of a user-defined stopping criteria. And the user can define this criteria in whatever level of complexity they want, and the tool will adhere to it. So GNAT coverage is our coverage solution at AdaCore. It will deal with statements, decision, MCDC. We use it within GNAT Fuzz to produce a coverage build such that we can get statement coverage analysis back to the user in near real time as we're executing the fuzzing campaign. We've also looked at a symbolic execution add-on capability. We're looking at a tool called SymCC, and this is an LLVM compiler pass. And we've produced an Ada version that adds a symbolic execution runtime into the fuzz test harness. And in conjunction with our GNAT LLVM front end, we can use this to explore more of the control flow and produce more test cases to pass back to the fuzzer. AFL has a very extensive API to allow you to customize the mutation engine. So here we can intercept the mutated test cases, and we can sanitize the data, or we can take full control and mutate the data with full awareness of the Ada types that they represent. And then we're working on an integration with our GNAT Studio IDE. So here we can analyze the Ada program, find what we can fuzz test, generate the harness, execute the test. And I'll show you a quick demonstration of that in a minute. And then, like all tools at AdaCore, it's fully invocable from the command line, and this allows you to integrate it into things like DevSecOps pipelines. So I just want to give you a quick demonstration of what that looks like. So here we're going to launch GNAT Studio on an Ada project. And we can see here that it is an Ada project. There's some Ada package specifications and bodies. And what we have now on the top right-hand side of the main menu is a new option called GNAT Fuzz. And we can use this to determine the subprograms that we can fuzz test. So at the moment, this fully working prototype will deal with parameters that are of discrete types. And we can decorate next to the subprogram signatures this new button for generating the harnesses. And we list all of the subprograms down here to show what we can fuzz test. So if we go ahead and generate a fuzz test harness, then we're immediately given the option to switch to that fuzz test harness project. And this is now wrapping the user project. So we can see the user project is still there, but we now have a fuzz test harness around it. And I can show you what a starting corpus looks like. This is a very basic one. It just says stop fuzzing when the statement coverage reaches 100%. But there's a lot of information we can put into these stopping criteria, and we can make them as complicated as we want. So we're going to go ahead and launch the fuzzing campaign now. This is going to produce all of the builds for AFL, for coverage, to generate the starting corpus. And we've generated 729 test cases here. And now we're going to minimize them down to the optimal size. And it's reduced them down to 4. So there's only 4 unique paths through all of those test cases. And then it's going to work out how many cores are available on the system. And there's 4. So it's going to launch 4 AFL fuzz sessions. And it's already given us the coverage feedback. And we can see it via that view, but we also get it decorated onto the code itself. So green means that line has been hit by the fuzzer. Red is a line that we haven't hit yet. And down in the bottom here, we have all of the test cases that the fuzzer has found has caused the Ada runtime to raise an unhandled constraint error. So what we can do with the test cases is we can expand them, and these are binary test case files, but we can dynamically decode them on the fly, and we can see what the types of the parameters and the data that was in them. And what we can also do here is that if we click on the test case, we can build the test harness in debug mode, execute the test with that test case input data, and we can get to the point where the exception was raised. We can look at the call stack, and we can work back down the stack if we want to, and we can use GDB as our debugger to work out what's gone wrong. And in this scenario, we will quickly find out that that particular calculation results in an overflow. And then we can fix the code and we can go back around the loop again. And we quite like this approach to fuzz testing. The motto at AdaCore is to build software that matters, and quite often that means making sure that the tools are in the hands of the right people. And as like with all testing techniques, the sooner you can get it into your software development lifecycle, the more benefit it's going to have. But saying that, we fully expect that for longer running fuzzing campaigns, we're going to need a client server architecture as well, and that's something else we're putting in place. Okay, so that was a very quick demonstration of GNAT Fuzz. I've just got time to show you, these are the references to some of the things I've talked about today. I can make these slides available upon request. Please do go and visit the AdaCore booth and the high class booth. And thank you very much.